There we go. We finished talking about inheritance, and we're going to move on to talk about lists. Now, for the most part, we're not going to get heavy duty into inheritance this semester, but we will be doing a little bit of it when we talk about lists. Because it kind of makes sense in the context, but also because it gives us a chance to do some inheritance stuff. So we're going to talk about lists. And there are different types of lists. We have like ordered lists, unordered lists. We might have a, I don't know, like a priority list, but I guess it's like an ordered list. Anyways, yeah, we can have a bunch of different types of lists, and we'll talk about those today. But yeah, again, before we get thrown into the lecture slides, are there any questions? All right, well, in that case, here's hoping all the people that aren't here are actually watching the YouTube videos. All right. Lists. So what are we going to learn? Well, what is a list? What's an ordered list? What's an unordered list? And what's an indexed list? And then we're going to talk about an array implementation and then talk about a linked implementation as well. All right, a list. Like a stack and a queue, it's just another form of linear data structure. And unlike the stack and queue, though, they're not as limited. They're much more general. So for those of you with experience in Python, it's a list, okay? You could, it's almost like you're treating it like a fancy extra super array, right? And lists are much more general versions of stacks and queues. So we'll talk about what makes a list, and then we'll start talking about different specific types of lists. But like there's literally potential for an infinite number of implementations and an infinite number of variations of those things, but we'll talk about a couple of easy popular ones, namely ordered list, unordered list, and an index list. And an index list, this is what you're used to in Python. So here's a list. You've got a front and an end. It might look a lot like a queue. And what things do we want to do with our list? Well, okay, we want to be able to add things, remove things, get the size, is empty. Basically everything we've done with the other linear data structures we've done so far. Now, when it comes to adding things, I suppose we have a couple of questions to ask. Do we want to like add them to the end, add them to the front, add them in the middle? Are there certain rules? Like maybe if it's an ordered list, we want the stuff to be like have the ordered preserved, right? If it's an unordered list, well, who cares? We can add it wherever we want. If it's an index list, well, maybe we want to be able to add it at a specific index. And when we remove things, well, how are we going to remove things? Where do we remove them from? These are going to depend on the specific type of list we're implementing. But we're going to want to get size. Well, that's easy, just how many things are in the list. And is empty, that's also pretty easy. But what else might we want to do? Well, take a minute and think about this. What things might we want to do? Well, if we were doing this in person, I suppose I would tell everyone to turn to each other and have a chat, but if it was in person, it would be hard to do this, and it's not in person, so let's just move on. So adding things to a list. Okay, so where? Where do we want to put something into the list? Well, that's going to depend. What do we want our list to do? Is it a specific type of list? Like, what are we doing here? Because when we talk about a list, it's a very general idea. And when I say we want to add something, you might have 1,001 different questions to ask in order to know where the best place to add something is. So let's start with an ordered list, because this is fairly obvious. An ordered list is a list where all the elements in the list are ordered based on some ordering. Some things in our universe have a natural ordering, right? Like integers, numbers, right? 1 comes after 0. 5 definitely is after 2, but it comes before 13. You know, like those things have an order. And some other things might not have an obvious ordering, and maybe we need to define an ordering for those things. Like imagine I had a list of like students, right? How do I want those students to be ordered? Do I want them to be ordered based on their current average? Maybe I want them ordered alphabetically. Do I want them ordered based on their height? Maybe their age? You know, like what the ordering isn't necessarily obvious. We might need to make a decision here and define the ordering we care about. It might depend on some characteristics, contents of the list. Yeah, okay, alphabetical order. Elements themselves determine the order of those things. So the things in the list know what their relative ordering is relative to all the other things that could be in the list of all this, like all the same types. So here's an ordered list, and here's the million-dollar question. If I want to insert 58, where does it go? No, wait, spoiler. Should it go? Oh no, where's my pen? Here it is. So let me ask you something. Should 58 go here? Well, no, because 16 is less than 58. And we want the things less than 58 to be like on the other side. So should it go here? Well, if I ask the question, is 23 less than 58? No. How about here? Is 29 less than 58? Wait, yes. Yes, so we need to keep going. Is 40 less than 58? Yes. Is 51 less than 58? Yes. Is 67 less than 58? No. Huzzah. We know it must go here. Why? Well, a moment ago, we had just said that 51 is in fact less than 58. So I know that 51 must come before 58. But then I found 67, and 67 is bigger than 58. Therefore, 58 must come before 67. And you might say, well, if I only know it's before 67, it can come anywhere here. Well, no, because we just did our linear search this way, and we had just previously concluded that 51 is in fact less than. So we found that moment, we found that instant where it belongs between these two. So it goes there. Whenever we add something into the ordered list, the rule is the ordering of that list must be maintained. Why? Because that's what it is. That's how it's defined. And if you say, but what if I actually really want 58 to come after 67 in a particular special case? Well, then it's not an ordered list. You're breaking the rules. So there's only really one way we can add something to this list. It's not like, okay, add to the front, add to the middle, add a specific index. No, whenever we add something to this list, it must go where it belongs. Yeah. So we can't specify where to add it. It just has to go where it goes. Can't just add to the end, can't add to the front. So should there be any rules on how we remove anything from this list? So should there be a rule saying that you can't remove from the front? Well, I mean, that doesn't really make sense. Why? Well, I mean, if we're removing something from an ordered list, all that matters with my ordered list is that the order is preserved. And if everything is in order, I don't think I can remove anything from that list that will break the ordering, right? Like if I go back here, like if I took 23 out, it's still in order. If I took 67 out, it's still in order. So removing doesn't really matter so much. Now, we could also have an unordered list. This is a different type of list. This is where the order of the elements, it's not based on anything. It's put in based on whatever I said to put things in. So if I want to insert this light blue square, and then maybe I want to insert this cyan or teal, whatever color that is, and then this black square, I can put them wherever I want. It doesn't matter. Why did I decide to put this here? I don't know, just because. I could have just as easily said, no, put it there. It doesn't matter. I can put these things wherever I want. New values can be inserted anywhere. Great. Should there be any rules restricting how we add something? No, we can add them wherever we want, right? What about remove things? I don't know. I don't think it should really matter so much, right? Like I can just take anything I want out of this list. It's a very arbitrary, general list. And then we have index lists. This is a third type of list. Now, also do note that when I'm talking about a list, I have a list, and then I have a sorted list, or pardon me, ordered. Then I have unordered, and then indexed. So these are all lists, but they're special specific types. So an indexed list is a list where the elements are referenced by a numeric position in the list. We're going to use zero-based indexing just like an array. We're basically making a better version of an array when we develop an indexed list. The number position is called the indexed. Wow, just like an array, yeah. Element position is important. Yeah, so the ordering is important. Sorry, not the ordering. Where I put things in the list will depend on the index and where I say to put things. Every time the list is updated, add remove, the indices of the elements will be updated. And here's what I mean. If I come along and add this here. You know what? I hate this. Why is this not starting at 0? 1, 2, 3, 4, 5, 6. There. If I added that, and then I added that, and then I added that, this is what I end up with, right? So this would become 0, then this would become 1, this would become 2, this would become 3, this would become 4, this would become 5, 6, 7, 8, and then this becomes 9. But of course here, for some absolutely ridiculous reason, I started counting at 1. Let me fix this because I hate it. It's driving me insane. There. There. So when I add things, we got to make sure the indexing order stays the same. Okay, so there are some operations that all of these lists have that are going to be like applicable to all of them, right? Like remove an element, adding elements. But the add is going to depend on the specific implementation, but they're all going to have an ability to add. Size is empty. They're going to be the same. So what's going to be some common list operations? Okay, well, I'll have remove first, remove last, and remove an arbitrary thing. You might say, well, is it really necessary to have a remove first, remove last, and then a remove an arbitrary thing where I specify a particular element? I don't know. I guess maybe not, because I could just specify whatever the first and the last thing is, but it might make things a little easier in terms of not having to search for stuff and whatnot. I'm going to want a first and last, because why not? Contains, this is a good one. This basically tells me if the list contains a specific element, because why not? You know, it's basically going to have something that'll do a linear search for me to tell me, does that thing exist? Why not build that into the list? Seems like a good idea. Is empty in size. But if I have an ordered list, my add is going to be a very special add that adds something in the correct place. There's only one add. There's only one way to add something to the ordered list. An unordered list? I don't know. I guess I could say add to the front, add to the rear, or add after a very specific element. Again, you might say, well, I mean, add to front might make sense if we have add after, but add to rear might not matter because I could just look for the last thing and then add it after the last. But again, whatever, let's just add it for ease. Then we've got our index list, we have add, but we're gonna have to specify a specific index here where we add. Set, that'll let us set something at a specific index, get something at a specific index, and then index of. This is basically like our contains, but it tells me not only that, like, okay, this thing does exist in this list, but it tells me the index where it is. And then our remove returns the element at a particular index. So if we look here, so this idea here, this is remove a particular element. So if I had like a specific person in my list, but then I would like look for this person to then remove. But this one, this remove looks like it's actually going to be remove something at a specific index where you specify the index. All right, a list. Given that there's a lot of commonality between these lists, let's use inheritance because why not? So we'll make an array list. I guess I could do a linked list. And I mean, we very well could do a linked list. There's no reason not to, but I'm going to do an array list for simplicity. No, I shouldn't even say simplicity. I'm just going to do an array list because why not? So here's what I'm going to have. I'm going to have some sort of list, and I'll have to have like a pointer to an array that's going to hold on to the stuff. And then I'm going to have a variable that keeps track of the rear, right? I mean, the front's always going to be index 0. So here's what we're going to have. And I'm just going to go and copy all this stuff. Let's see, I'm gonna get rid of rectangle, get rid of rectangle, get rid of square, get rid of square. I'm gonna add new class. And what did I just call it? List. This is the header, perfect. Nope. There. So here we go. You know, we're going to want it to be generic. So, you know, we're making the template class. So everything's going to be written in here. I guess our list CPP is probably going to be pretty empty. Okay, so we got that. And we've got our private. So I guess my default capacity is set to 100. Why? Because. So what this is if in my constructor, I don't specify a particular size I want my array to be built, it'll just call the default capacity. Now you'll see I'm using protected. And you might remember in last class, I briefly talked about the idea of the protected keyword. It's basically, for our purposes right now, it's kind of like somewhere between private and public. And the reason I'm using it here is because it's going to give us access in child classes to these things directly without having to use some sort of special getters or setters or accessor methods. So the protected is just going to make that a little easier for us for learning purposes. And then here, public, I've got my constructor, my copy constructor. I guess I don't even have a constructor where I specify size. My deconstructor, remove first, remove last, remove first, last, contains, is empty, size, whatever. I've got all these things, we're gonna have to implement it. And you might be saying, okay, what's the shift up, what's the shift down? Well, we'll see in a moment, but it's gonna be pretty handy. Yes, so that looks pretty good to me. Are there any questions at this stage about what we are seeing? Happy to answer them. I suppose I should actually just go back to what we are seeing to see if you do have those questions. Here, I'm going to zoom up just a tinge. There. So we just got our size, capacity, this. So we have to have this capacity, know how big the array is. That makes sense. Expand capacity, this looks familiar. Find, okay, that's just like the search. But I mean, shift up and shift down seem a little funny. Contains, find. I wonder, there's probably some sort of relationship there. But shift up, shift down. I mean, it'll be obvious once we get there. But anyways, we got our is empty, our size. Looks pretty good. This looks like we're hitting all the things we need. Great. All right, so what should our constructors look like? Well, okay, so our default, we'll set the capacity to default capacity, set the size to 0, and then make a new pointer to an array. Or actually, no, the pointer to the array already exists. Make a new array and have the pointer point to that new array of size capacity. And then we've got our copy constructor. And remember before, when we asked the question, how deep are we going to go? Well, what's reasonable in our situation? Here's what we're going to do. We'll copy over the capacity and size, we'll create a new list, but then we're gonna actually copy over the contents of the array from the other thing. Because, I mean, I don't know what the thing of type T is. Is it something that needs to be copied deeper, or is it just integers, you know? And then here, our deconstructor, all we need to worry about is deleting the thing that our list pointer points to, that array. And as before, we don't need to worry, this particular class isn't going to be the one responsible for deleting the contents of the list, because if those things are objects, pointers to objects in dynamic memory somewhere, I'm not responsible for deleting that. Someone else created them somewhere else in the code, maybe in the main function, so they're the ones responsible for deleting. And here, our expand capacity looks pretty standard based on what we've seen. Just double the capacity, create a new array of twice the size, copy over the contents, delete the old list and set the new list to be pointed to by the old list pointer. Okay, our shift down. So what's actually happening here? What is this code doing? Shift down. So I specify a start integer, and then I go from start, well, I is less than size minus 1, I plus plus. Now, here's a quick little quiz. Have a look at this code and tell me what you think this is going to do. Like, what does this code do? And why is it size minus 1? This size minus 1 is, you might find it obvious, but this actually comes up as something that trips up new programmers a lot. In fact, I had a friend finishing their master's who had a really hard time. They had some code, but they weren't a programmer, they weren't a computer scientist, but they were using Python. And he was having some issues with debugging. And after hours and hours and hours and hours of looking at the code, I had discovered it was basically this issue. And I mean, I wouldn't think to look for it because it's a very like, this is a common beginner mistake, but less so later. I mean, that's not to say that these errors don't pop up later. It's just I didn't think to look at this because why would you make this mistake, right? But anyways, it'll get you. So, and I mean, does anyone have any ideas of what this code is doing? All right, let's see. What do we have? Shifts all the values, shifts all the one to the left. Actually, I think it's gonna be one to the, wait, why is everyone shift one to the left? I think it's gonna be shifting the values to the right. And the -1 is not because we're starting at index 0, because we're taking care of that with the less than. No, you're saying I equals I plus 1. Yeah. What? So it would get the value next in the, so it would get the value next in the list. Oh, okay, so hold on. Oh, you're oh my goodness, how embarrassing. How embarrassing. I think you're all right. Shift down. And you know what? That seems to be appropriately named. So let's have a look at what's happening. If I have the old array, actually, let's make sure I don't have some, no, okay, I don't. If I have the old array, or not the old array, the array. And so it's 0, 1, 2, 3, 4. So what is this saying? If I start, let's say start is 2. Okay. So if start is 2, and let's say size is 5. Yeah. So start is 2. So start, size 1. So this is size. So what are we doing? So 2 is 2 less than 5 minus 1? Yes. So what are we going to do? List at I, so list at 2, becomes whatever list at I plus 1 is. All right, so just move that down. Increase I. 4. Oh no, 3. Is 3 less than 4? Yes, so copy what's in I plus 1, which is 4, down to 3. And then we go to 4. Is 4 less than 4? No. Okay, so we stop here. Basically, the -1 here is to protect against this edge case, because we do the -1, but we have the +1 here. Anyways, long story short, so to the left. Yes, you're right. I messed that one up. Michael and Johannes were absolutely correct. I jumped the gun and wanted to tell you all you were all wrong when you were actually all right. So my mistake. My apologies. So presumably, shift up is going to do the opposite. So there we go. Start at size. Basically, it does the opposite. We just move things up the array. If you're wondering, well, hold on, shouldn't shift down, you know, you're moving things down the array. I know that could set like that. If you're ever confused about, wait, which one shift up, which one shift down? The way I like to think about it is shift down based on the indices. Shift up based on the indices. So you're moving things up to higher indices, or you're moving things down to lower indices. That's what I like to think of. So because 0 no longer exists, so it's effectively shrinking it, I think, unless it was linked. What? Why doesn't index 5 go to 4? Because 5 didn't exist, right? And because we start, well, it's not because 0 doesn't necessarily exist. Remember, let me clear this out again. So remember, if we didn't have this, right, and size is 5, that means we have 0, 1, 2, 3, 4, 5, 6, 7. That one exists, right? So 5 is the size. But remember, this is 1, 2, 3, 4, 5. So the last thing is 4, right? One size is 5. But what would happen if I went all the way to less than 5, right? So in my previous case, I started at 2 and went all the way up to size -1. But now let's go all the way up to size. So if size is 5, we will go to 4. So I will become 4. And then I will say, copy into index 4. What is an index? What's at index 5? But what's at index 5? Well, I don't know. It's not really in my list. I don't know what's in that index. It's garbage for all I know. It's a random series of zeros and ones that just happen to be in that memory location. So we want to do size minus 1. And if you're left going, but wait, but why? If you're looking for how those dots connect, it's because when we have the size minus 1, we are taking size plus 1 here in that last case, which would then be like that. So size is 5, 4 is less than 5, but then if it's minus 1, we get to 3, but this is 4, right? So the plus 1 here, because we needed this plus 1, we needed the minus 1 here. And if you're ever thinking of this again too, another thing I like to think about is whenever you're doing something between 0, 1, 2, 3, 4, 5, 6, 7. Like if I asked you how many things are in this array, you would say 8, right? 0 through 7. But, you know, this loop isn't so much putting its finger on each thing in the array as it is, let me just erase these. No. Let's see if I can fix this. Sure. It's not that we want to put our finger on each index in this array. What we want to do is basically it's how many pairs of things are there? How many adjacent pairs of things are there? So we've got 1, 2, 3, 4, 5, 6, 7, right? So how many things are in this array? Well, 8, because 0, 1, 2, 3, 4, 5, 6, 7, that's 8. But how many pairs of adjacent things? 7, minus 1. So we want to loop up to like the number of adjacent things. And if that doesn't help you and that just confuses you more, then pretend I didn't say that and ignore it. But you might find that helpful because that's what I like to think about. Yeah. So shift up, shift down, yeah. And if you're ever confused, which one shift up, which one shift down by the indexes. Shift up indexes. All right, find. All find is gonna do is a linear search. So for I in range 0 to size, if list at location I is the thing I'm looking for, this assumes that they're comparable with equals equals, return that index. But if we ever finish this loop, if this loop ever finishes, that means we never called this return. And if we never called that return, we therefore never found the thing we were looking for. We'll return -1. And -1 will be like the special value we get. If we ever call find, that's supposed to tell us the index of where something is. If we ever not find it, we'll return -1. And that's a special value that we'll keep track of. Sometimes what people will do is they'll set this as a constant to be like not found. And they'll define it at the top of their code somewhere, and then they'll return not found, so the code becomes that much more descriptive, but I was too lazy to do that here. There's people walking around outside. That's why I'm getting distracted. Remove first. Okay, well, we'll have our classic is empty, throw an exception. Otherwise, get the elements at location 0, shift everyone down to 0, decrease the size, return element. And look at this. Look how much cleaner this remove first comes as soon as we have this special method here, right? Remove last. Well, this one's a lot easier. We don't have to shift anything around, right? We just, you know, check if it's empty, get the last thing and decrease the size. That one's much easier. And then we've got some remove an arbitrary thing. So what are we looking at here? If it's empty, again, just, you know, okay, fine. Otherwise, find that value. If the index comes back as -1, which we just talked about, well, we'll throw another exception, saying like, okay, no, it wasn't found. Otherwise, if we find it, well, just return, like get the thing at that specific index of where it is, shift everyone down to that index, decrease the size, return the element. There. I know this one looks far more complex, but if you just take your time, what is it? Is it empty? Yes or no? Okay, fine, great. Find where it is. Is it not there? If it isn't, well, throw the exception. Otherwise, we know where it is. It's at index, and then it's basically remove first, but instead of 0, it's the index that we found it at. First, okay, great. Last, great. Contains, this one's easy. If we already have our find function written, just find it and tell us true or false if the data was found. Or basically, did find not return -1? If find didn't return -1, well then it's in there. Size, return the size. Is empty, is size 0. That's it. That's going to be our base class. All lists are going to have these in common. So what I'm going to do now is I'm going to copy all this over to my list header. But as I'm doing that, think of any questions you might have, and we'll see if we can answer them. All right, so those are copied. Our deconstructor, not overly complicated. Our expand capacity, looks like every other expand capacity. Shift down. Shift up. Fine. Whoa! What? What did I do? I think I hit Control W by accident, which closed it. Shoot. All right, well, let's get this back up. All right, yes, let's resume. Oh. Okay. Copy the shift down, shift up. No, I already did get shift up. Okay, find, remove first. No, remove last. Our general remove, where it takes a specific thing. And then first, my goodness, there's a lot here in the base class, but that's good, right? Because then we don't have to re-implement this in the subclasses, in the child classes. Contains. Size. Is empty. Oh my, okay. I mean, it's a lot of lines of code, but you'll see that, I mean, no one function is crazy, right? Like shift down, like it seems complicated, but look, I mean, really, it's not that bad. So all these things, they do a lot of sophisticated work for us, but there's not a lot of code here. There's not a lot of actual magic happening in the back. And the great thing is, like when we see the index list, you'll have a much better idea of how the index list is actually implemented in Python. Like in the back, as soon as you open up the hood type thing. Okay, so that's, okay, it's kind of useless. There's no way to actually add anything yet. Yeah, because the list class is basically, it's so, like, you can't have just a list. You're gonna have a specific implementation of a list where you can add things a certain way. All right, were there any questions about what we have seen so far about the base class list? If you don't ask questions, I'll assume, pardon me, I just burped. I'll assume you understand everything completely up until this point. And I mean, that's amazing if it's the case, but that's atypical for 162. All right, okay, keep up the good work. Oh, here we go. So just like an array class, At this point, it kind of is, right? Like an array isn't defined, like there's no array class, right? Well, there's the standard array library, right? Or there's the standard array, but like if we're thinking of our basic arrays of just a contiguous chunk of memory that we allocate, then like we're building on top of that. We're making a better version of it where we can ask, like if it's an indexed list, we can ask that list, hey, do you contain this thing? Hey, do you have, it's the same as array list in Java, I'm guessing. I mean, yes, it literally is. I mean, that's what we're building. And if you go look at the array list class, take a wild guess at what you're gonna see in that class. Like array list, sure, you got it for free, right? And same with in C++, you know, you'll have vectors, right? You'll have those. And in Java, you can import a queue. You can import a stack. Like you can import all these things, but someone had to write them. So we're writing them right now. So Michael, you're absolutely correct. It is just like array list. In fact, if I were making this class, I probably actually should have called this class array list, not just list. In fact, can I rename this? Rename. Is it going to ruin everything? Array list. No, I probably should have done the header. Oh yeah, okay, it worked. Sweet. Perfect. There, it's an array list. And you know, the convention I'm following is, okay, what's the container? What's the data structure? All right, are we supposed to see code? Yes, you were. My God, I'm still so bad at this. There. All I did was I renamed list to array list. There. That's all you missed. So there, we've got our array list. It's not particularly interesting at this point. We're gonna make an indexed array list, I guess, soon. But yeah, that's, you're absolutely right, Michael. It is an array list, but we're building it. In fact, it's always amusing because you'll have, and I'm not suggesting you did this, but every once in a while, it would always happen where, and this hasn't happened at St. FX, but it always happened back at Western when I was teaching. You'd have one student that would show up when I would be teaching like how to build a list or how to build a queue or something. They'd be like, why would I do this? It's already implemented. I can just import it in Java. I'm like, yes, but that's not the point. You're learning how to build these things. You know, so you always get someone that wants to show off, oh, I know about this super special class that's already implemented that I can import. Fantastic. And like a student got into an argument with me saying like, no, you shouldn't, like if we're building the array list, why aren't you, like, why use an array? Why not use an array list to build an array list? And then it's like, but the point is that you're supposed to pretend that array list doesn't exist because you're currently inventing it. Anyways, it ends up being something, but actually it's never happened at St. FX. People aren't trying to, they're not doing that weird showboating stuff. So keep up the good work and don't be annoying. Any other questions? Any other questions? And hope, oh yeah, so yeah, Johannes, you were asking about the array class. I mean, we're basically making a better version of an array when we make specifically the indexed list. Yeah. All right, I'll carry on then. Oh, too far. All right, so it's useless. So let's make, oh look, I even called it array list in the slides. My goodness. So I'm gonna make an array ordered list now. All right, and it's going to inherit from array list. So let's go here. Nope, no. Class, add, class, okay, array ordered list, and the base class is array list. Okay, great. Look, it already did that for me. Wonderful. But I'm super lazy, so I'm just gonna do this. Great. So what private attributes are we gonna need? Nothing new here. We're not going to need anything new, but we're going to have to implement our constructors, and we're going to have our add. Otherwise, we're just going to use what we inherit for free from the parent class, array list. Because add is the only unique thing for the ordered list. Because the rule is whenever we add, we have to insert it in the right spot. So what is this going to look like? Oh, yeah. So what are the constructors going to look like? Well, they're just going to hijack the parent class's constructors. Nothing particularly fancy. And we'll just call the parent classes Deconstructor. There we go. And add. This is it. This is all add's going to do. Now let's take our time and have a look at this. All right. If the size is going to be equal to the capacity, basically, have we run out of room? If we have, expand capacity. And you know what? Expand capacity already exists because it's defined in the parent class. Ooh, array list. I did see a potential issue here. Yeah, this is array list. There. Yeah. So yeah, expand capacity is defined right here. Call it from the parent class. Wonderful. Otherwise, start at index 0, and we're going to do a linear search. Well, index is less than the size, and the thing we're looking for is currently bigger than the thing I'm looking at. We're going to count up. If you're saying, why not just do this in like a for loop with a break? I mean, we could. There's no reason, like there's no rule saying this needs to be a while loop. But basically, this part of the and is just, is there still stuff left in the array to look at? If there is, great. If there's not, basically, did we get to the end and not find anything that met our condition? And then what's this? If the thing we're currently looking at is less than the element, is that right? If the thing I'm currently looking at is less than the element, is less than the thing I want to add, yes, then keep moving down because this must come after. Right? If we ever see the situation where the thing I'm now looking at is bigger than the element, now I found it. Now I know where it needs to go. So I will stop because the condition's not true, and index will be where that new thing needs to go. Then I'm just going to shift everything up, starting at that index to make room. If I've got this array and I want to put the thing right here, well, I'm going to have to move everything over here so I can insert there. And then add that element, increase the size. If this seems like it's hard to chew on, let's draw it again. And wait, I am sharing my screen, correct? And I'm not, okay, good. So what's, this is horrible. So like, what is this saying? Well, this part, we can ignore this. This is basically, okay, are we at the end? Because if index is not less than the size, well, there's nowhere more to go. And then we would just basically insert at the end at that point. So like, what's going on here? Well, let's draw it again. So if I have the numbers like 1, 7, 14, 21, 96. Let's add another number here, 8. And I want to come along and add the number 11. Okay? I would go look at this. Okay, is the index less than size? Yes, because the size is 1, 2, 3, 4, 5, 6. Size 6. So is the thing I'm currently looking at 1 less than element? Yes, it is. So we know that the element 11 needs to be after this. Okay, so we increase index. All right, now we're looking at 7. So is index, which is now 1, less than 6? Yes. Great. Is the thing I'm currently looking at less than element? 7. Is 7 less than 11? Yes. All right, keep going. 8. Is 8 less than 11? Yeah. Now we're looking at 14. Is like this is obviously, we're okay. Index is less than size. So is 14 less than 11? No. So what do we have to do? Well, we're going to shift, we're gonna have to shift this down one. So we're gonna, here, let's do it this way. I'm gonna have to take the 96 and move it down one. I'm gonna have to take the 21 and move it down one. I'm gonna have to take the 14, move it down one. Ugh. Let's do this again. There. Now I can take my 11 and go, yep, there. Oh, and I guess I'll draw off the comma. And you might say, but what if we ran out of room? Well, don't worry, we wouldn't have, because we already checked. If we add something, are we gonna run out of room? And we'll have expanded capacity already. So this is wonderful. And if we ever get to the point, imagine for a second that I'm trying to insert 100. I would go all the way to the end until index becomes size, basically 8. Actually, no, 1, 2, 3, 4, 5, 6, 7. Wait, 1, 2, 3, 4, 5, 6, 7. Yeah, so 7. Index would become 7. Is 7 less than the size? No. So that means it must go at index 7. So 100 would go here. Hopefully that helped. Any questions about that? If you looked at this and you're left going like, wait, what? Honestly, draw it out. Open up Microsoft Paint, grab a sheet of paper and a pencil and draw it out. It'll make sense. It can seem like there's a lot going on here, but if you break it down, I always say, there's no magic rule. The only rule is, what does the code say? And then if you follow it correctly, you'll know what it's doing. There's no ifs, ands, or buts about it, because that's how a computer works. So, any last questions before we wrap up for the day? I'm a little concerned that we have basically a third of the class showing up to lectures. Hopefully those that aren't showing up are doing just fine and they just feel the need not to come to lecture. So, yeah, anyways. So, okay, seeing no questions, I'll see you all later. I'll see you all tomorrow and enjoy the rest of your day.